In this video, we're going to finally finish the Rossby Wave problem that utilizes quasi-geostrophic potential vorticity that allows us to analyze mid-latitude Rossby waves, what they're like, how they depend upon their stratification, their wave dispersion relationship, all the equations shown for you, including their propagation speeds. That's today on High Peak Education. Thank you everyone for watching. Greetings to you. Hope you're having a wonderful day. And I heard from a listener that they really wanted this video to be shown. And so what I'd like to do is I'd like to record this. So hope that you're ready for this. We've got lots of math coming today. We've got really just a treat here for you. We're going to do parts B, C, D, and E, but we're just going to call this video part 2B because it's going to finish the rest of the problem. We're still going to use the predictive quasi-geostrophic potential vorticity equation in terms of that perturbation stream function that we had before, and we're going to substitute in a complex waveform and see what a wave-like disturbance does. So without any further ado, let's get into today's video. So here we have part B of the solution, and I'll go through the rest of the parts of this problem so that we can understand, now that we have the quasi-geostrophic potential vorticity written only in terms of a stream function, we'll be able to answer the other parts of the question. So let's have a look at part B. It says, consider a wave-like disturbance psi prime equals psi tilde z exponential raised to the I of kx plus ly minus omega t, and assume that the vertical structure psi tilde of z satisfies d by dz f naught squared over n squared d by dz of psi tilde equals capital gamma squared psi tilde. Show that the dispersion relation is omega is equal to minus k beta over k squared plus l squared plus gamma squared. Okay, so a couple things here. First of all, I've called equation 25 and 26 just these two relationships that you see here and you see here. Now, what are all these symbols really meaning? Now remember, psi prime is the perturbation stream function. Remember, the stream function means that this flow we assume to be divergence or convergence free. So it's a perturbation, the stream function. And remember, the stream function is going to be somewhat similar to the change in the geopotential height as a perturbation. So because that's what drives these winds and so on and so forth. Anyway, notice that the amplitude sort of out front of this wave-like disturbance does depend upon height. So that's psi tilde z. And then exp, so exp of a quantity is like e, the natural exponential to that quantity, where of course e is approximately 2.718 and so on. That's so-called Euler's number, so the natural exponential base. Remember that I is equal to the square root of -1, so it's the imaginary number. And the question is, why do we raise to this imaginary number with this phase? Well, because when we use a complex exponential by Euler's formula, we can get cosines and sines, and we can move through not only the real but also the complex plane, and it's just a much more compact way of writing a possible oscillatory wave, namely sines and cosines. Okay, so k is the horizontal wave number in the east-west direction. L is the meridional wave number in the north-south direction. So k and L both have units of radians per meter. That's why they're called wave numbers. Now notice, because these wave numbers are in the denominator of this equation, notice that capital gamma will also have the same units, namely radians per meter in terms of its units that it has. Okay? And so capital gamma here is going to act like a wave number. By the way, omega here, so omega is the angular frequency, and that's going to be units of radians per second. The idea is that this psi tilde, which depends upon height, is going to go into this stratification term, because we know that as we go to different layers, depending upon how psi tilde changes, the stream function will change in different layers, and there's basically going to be more or less like a vertical wave number. So think of capital gamma like a vertical wave number. Okay, so that's effectively what it is. Now, by the way, what in the world are wave numbers? Well, hopefully you're aware that if you have any wave number, say k, and remember k is in the x direction, that would be 2 pi over lambda x, and lambda x is the wavelength in the x direction. So if you have long wavelengths, you have small wave numbers, and if you have short wavelengths, you have larger wave numbers. Okay? By the way, typically things like Rossby waves, if you've seen some of the thumbnails in this video, there might be 5 or 6 or something around, say, the northern hemisphere in the middle latitudes. So K would have the number, say, 5. So wave number 5 is sort of this standing wave pattern of Rossby waves. Now, notice, what is the dispersion relationship? The dispersion relationship tells us the relationship between the angular frequency, that's how often the waves oscillate in time, and the wave numbers, which has to do with the size of the waves. And for that matter, this dispersion relationship is going to allow us to calculate the phase and the group velocity. So in other words, the speed and direction of wave propagation, either the signal or the energy. Okay, so anyway, notice that these tildes, by the way, should be over top of these psi's right here. So sorry, that's just the typefacing. But anyway, there are these two equations written, namely equations 25 and 26. By the way, you can also think of capital gamma and these k's and l's also as like normal modes. So if you're familiar with Fourier analysis, k and l are sort of like the wave numbers that go along with the various spatial frequencies in either x, y, or z. So east and west, north and south, and the vertical. Okay, so you could also think about these as sort of normal modes, or sometimes called eigenvalues, right? So if you're familiar with eigenspace and eigenvalue analysis, eigen is the German prefix for sort of like unchanging, and the idea is that, yeah, I mean, basically, it's the sort of like a perpendicular direction, if you will, and the eigenvalue only tells you how much you go in that direction. It's invariant under the transformation. There's more to be said about that. But anyway, let's go on to the next slide. Let's think about how we're going to do this. Well, what we're going to need to do is we're going to need to use this wave-like disturbance, namely equation 25, and we're going to need that in the Quasi-Geostrophic Potential Vorticity predictive equation. We're going to need to insert that for psi prime. So let's see how that's done. Substitute the waveform, which is equation 25, into the predictive Quasi-Geostrophic Potential Vorticity equation, which was equation 24, and solve for the angular frequency omega to find the wave dispersion relationship. Okay, so I'm going to toggle back a couple times, and let's see how we get this expression here, equation 27. Notice that here we have x and y derivatives of psi prime. So when we take derivatives of exponentials here, we notice that it's the same exponential, but either k or l is going to drop down along with the imaginary number I. So that's exactly what we see here. We see I squared, k squared, and then psi prime, because the entire exponential and all the other parts stay the same. Then we have I squared, l squared, psi prime. Okay, now what happens with the vertical term? So in this vertical term, we got to do d by dz of psi prime, which only really is the derivative of psi tilde. Because remember, psi tilde is the only thing that depends upon z. The whole rest of the thing is just the same. So we have this complex exponential still here, And then we need another time derivative. Sorry, we need another vertical derivative of that. We're assuming that f naught squared and n squared are right there like so. Okay, so there it is. And notice that this complex exponential can come out front. And then what about this term? Now this term comes from the beta term. So if we do the partial derivative with respect to x of the psi prime, notice that a minus k drops down and then beta is still there. Remember, beta is the north-south derivative of the Earth's Coriolis parameter. Remember, that's df dy. Oh, and there's also still psi prime, because remember, when you take derivatives of exponentials, the same exponential appears. Now notice, do you see how this complex exponential is in all of the terms? So we see this here, but it's not in this term, at least not directly. So we'll get to that in just a second here. But notice, we'll be able to get rid of that or something like that very soon here, because we're going to assume that psi prime is not 0. So we'll come back to that. Next, what about any of these I squareds? So I squared, since I is the square root of -1, I squared is just -1. So hence we get a minus here, and then we get a minus here. And notice that, how about taking minus omega out? Now what's going on there? We still have the time derivative that we have not done yet. So think about this. We still must do this d by dt of all these terms. So since each of these is a psi prime, the time derivative of, say, something like this makes a minus I omega pop out, just out front. Hopefully you see that. The complex exponential remains the same. Notice we could also move this term, the beta term, to the other side of the equation. Okay, now notice that each of these terms has a negative on it, but we also see that there's a minus on this side now. So let's leave the minus on this side. Let's have the minus sign go into all of these terms by distribution. So this minus is going into all these terms. So we have I omega k squared psi prime squared plus L squared psi prime squared. And then let's actually take the vertical derivative of this. So we take the vertical derivative of this. Let's assume that we can just replace that. In other words, we're going to replace that from equation 26. So this right here is going to be equation 26. And remember, equation 26 was the eigenvalue, this sort of capital gamma, as sort of a normal mode. So this entire thing right here just becomes minus gamma squared psi tilde, like so. So that's just substitution from equation 26. Notice when the minus comes in via distribution, minus times minus, that's going to give plus. Also notice that psi tilde times this complex exponential, that's going to be able to reassemble into a psi prime. So remember, we're going to divide the entire equation through by the non-zero complex waveform and solve for the dispersion relationship. So psi tilde times a complex exponential is just psi prime. So this term right here, as you labeled, is psi prime. And notice that minus times minus is plus. And remember, psi prime has to be not 0. Otherwise, we don't have a wave. So if we divide through by psi prime, just, it's not 0 and all the terms have it, you should just get this. So our expression is getting a lot easier. So it's I omega k times k squared plus L squared plus gamma squared equals minus I k beta. Well, you can divide out the complex number I from both sides, and then divide by this k squared plus L squared plus gamma squared. So notice we do indeed get the expression we were looking for. So this is the dispersion relationship. So most of you that have taken introductory wave analysis classes have dealt with non-dispersive waves, which means that depending upon their wavelength, waves don't move at different speeds. But in this particular case, we see that, well, let's think about this. If K or L or gamma are large, that's large wave numbers, that means that if we have large wave numbers, that means by definition then the wavelengths are small. So if we have small wavelengths, then we get large values of this fraction, and thus the idea is that the phase speed is going to be large. That is, the propagation speed of short waves, of small wavelengths, is going to be relatively fast. Notice also this minus means that, I think this denominator is always going to be positive or zero. It's probably not going to be zero as long as we have an actual wave. So if the denominator is positive, beta is going to be, let's say, positive. So at least in the northern hemisphere, when you go towards the pole, it's going to be positive. So that means what we're going to have, as long as k is a positive, we're going to have a negative. So what that means is Rossby waves will propagate towards, let's say, the west. Okay? So what does that mean? That means that a Rossby wave, in most situations, at least longer wave Rossby waves, are going to move towards the west because you have this minus sign. Okay? So I hope that kind of makes sense. Typically, in the middle latitudes, Rossby waves propagate west if the background, they propagate towards the west if the background geostrophic wind is very small. But if the background geostrophic wind, that's west to east, causes them to be nearly stationary, then we can have stationary Rossby waves. So when a Rossby wave moves towards the west, we call that retrograde. When a Rossby wave moves towards the east, it's propagating, but we can also have Rossby waves have about zero propagation speed. Okay, so I hope that makes sense for part B. Let's have a look at part C. Show that the frequency of the barotropic mode is independent of stratification. So, independent of stratification is a key phrase, and then we also want barotropic mode. Now let's see if we can talk about that. Let's define a barotropic atmosphere. So the technical definition of barotropic atmosphere is that the pressure is a function of density only. What's that really mean? It really means that as you go upward in the atmosphere, that pressure only depends upon the density. In other words, there are no temperature gradients on a constant pressure surface. So that's the technical definition of a barotropic atmosphere. In other words, pressure is only dependent upon density. In other words, there's no baroclinicity. Okay, no baroclinicity. In other words, if you looked at, let's say, height lines, let's say these were geopotential or height lines. Okay, so you can imagine this is, so let's call this capital Phi 2, capital Phi 1, and capital Phi 0. So these are, let's say, geopotential lines. The isotherms, that's the lines of constant temperature, are going to be parallel to these. There's going to be no baroclinicity. In other words, depending upon where you are on the Earth, as you go vertically upward, only density changes to change pressure. Okay? So there's going to be no vorticity. There's going to be no twists. Okay? So the idea is that there's going to be no kinks. In other words, you're not going to create any low pressure systems. Okay? I'm trying to say this several different ways so that you kind of know what I'm getting at. So this is the definition of a barotropic atmosphere. Now we're supposed to show that it's independent of stratification. What does that mean? Well, stratification means in the vertical. So typically the atmosphere is stratified in the vertical. Okay? So what we're going to assume is that if we're barotropic, that the psi prime does not depend upon z. So that's exactly what I'm writing here. That psi prime b is only a function of x, y, and t. So let's plug that in to equation 26. So remember equation 26, and that was the definition of the sort of vertical mode, the capital gamma squared. Well, if you plug psi prime into this equation, notice that this vertical derivative right here is going to be 0 because psi prime does not depend upon z at all. Okay? That's to say that it's going to be independent of stratification. So you're going to get 0 here, and we're assuming psi prime b is not 0, that the wave disturbance is not 0. So it turns out the wave disturbance will only depend upon north-south or east-west perturbations. It won't depend upon the stratification. So it won't depend upon how the pressure surfaces change or whatnot. Okay? So you would get gamma equals to 0. So this solves part C. Hope that makes sense as well. Let's now have a look at part D. It says, consider baroclinic modes. So psi tilde of z are going to equal cosine of n pi z over h. Find the dispersion relation of the nth baroclinic mode. Okay? All right, so a couple things here. First of all, what that means is, what would psi tilde of z look like? So imagine this is the direction of psi tilde, and suppose this is the height. So I'm just sketching sort of an axis here. Suppose you have the first mode. So let's do first n equals to 1. We don't want to do n equals 0 because cosine of 0 is 1, and so that's not really much of a mode. But if n is 1, what that means is you have a pure single cosine wave. I actually drew more like a sine wave here. Notice that cosine starts at its maximum value when z is 0, and cosine's up at its maximum value again when we are at pi. But when I say pi, when z is equal to h, then you have like that n pi, and then n pi, cosine of pi is -1. So really, actually, I should have drawn it like this. So we start off at the maximum value here, and then we go, so it's like a cosine wave, right? We're going to go through 0, and then we're going to end up over here. Okay? So here's h over 2, and then here's height 0. So we go from max over here to min. So this is the minimum value. All right. So the next cosine wave is just going to have twice the frequency. Now think about this. So if you do n equals 2 mode, we still know that when we have the n equals 2 mode, when z equals 0, we're at the maximum value. And then when z equals h, we're actually back to the maximum value, because that's like the cosine of 2 pi, which is the same thing as cosine of 0, which is maximum value, like it's 1. Now notice, it's still going to go through 0, but then it's going to go down to here and then back. So I think the second mode is going to look like this. Something like that. I didn't draw it extremely well. In fact, I actually think it should be down here at its minimum when we're at right there. So, and then it should go through this point, it should go through this point. So again, I'm trying to do my best to draw this sideways. Really doing my best. Okay, so anyway, there it is. Has twice the frequency. Okay, 2 times the frequency. And then you could keep going. The next one would have 3 times the frequency of the original, and so on and so forth. So basically, these are like Fourier modes. So n can be the value 1, 2, 3, and so on. And notice that they're just higher and higher frequencies. Let's assume that n squared is constant. Typically, capital N here, the Brunt-Weissler frequency, does depend upon height. But let's just assume for the simplicity of this problem that n squared is constant. So let the Fourier mode version of this stream function vertical structure be psi tilde of z equals cosine n pi z over h. That's equation 38. We want to substitute that into the definition of gamma squared. Remember, gamma squared kind of gives us this, right? This equation 26. So let's do that here. We're going to have, and again, let's just pull these terms out, the f naught squared and the capital N squared, the Brunt-Weissler frequency, and just do two derivatives of this cosine n pi z over h term. Because, well, why is that? Because this is psi tilde equals negative gamma squared, here's another psi tilde. Okay, so what happens when we do two derivatives of this? The derivative of cosine is negative sine, and the derivative of negative sine is negative cosine. So we get a minus and then a cosine here. But two z derivatives, n pi over h popped out and n pi h popped out. This is n squared pi squared over h squared pops out. Now notice it equals this. Now you'll see that these two cosine terms do cancel, and we can solve for this minus gamma squared. So we get gamma squared is equal to, notice everything here is squared. So that's n pi f naught over nh squared equals gamma squared. Or you could of course say that gamma is just equal to n pi f naught over, and this cursive n, which is the Brunt-Weissler frequency h. Okay? So there we go. So notice, now let's plug back into the dispersion relation. Remember the dispersion relationship was equation 32 here? So back to equation 32, notice that we can get the dispersion relationship with this nth Fourier mode. So now we're just plugging in for gamma squared. So there it is. Now notice, that's kind of an interesting thing, because what that means is the higher the frequency, so the higher the value of lowercase n, that means the bigger the denominator, and thus the slower propagation of these modes. Okay? So hopefully that kind of makes sense how we analyze this. By the way, if h is larger, so if we have a taller atmosphere, then we have a smaller denominator, and thus the modes propagate faster. So overall, this dispersion relationship gets to be a larger magnitude. Okay, lastly, part E. Remember, this is a pretty tough problem because this was originally a comprehensive exam question. Estimate values of the parameters for typical mid-latitude Rossby waves. Calculate the phase speed of the barotropic mode and the first baroclinic mode. You may use the constants of n, that's capital N, that's the Brunt-Weissler frequency, is about 10 to the minus 2, so that's 0.01 seconds to the minus 1. F naught is about 10 to the minus 4 seconds to the minus 1. That's roughly a mid-latitude value of the Coriolis parameter. And then a mid-latitude beta value is about 1.6 times 10 to the minus 8th, 1 over kilometers, 1 over seconds. Okay, so let's start working a couple things out here. First of all, the wavelengths of mid-latitude Rossby waves by observation tend to be about 5,000 kilometers. Okay, that's approximately. We're talking sort of like the width of North America, if you will. We know the distance from San Francisco to New York is roughly 3,000 miles, so about 5,000 kilometers. I mean, I'm really ballparking things here. But remember, that's about 2 pi over k and 2 pi over L if we're talking the zonal or the meridional wave numbers as part of this. And then, so this is, again, mid-latitude Rossby wave wavelengths. This is a typical scale height. So when I say a scale height, this is the typical depth of the troposphere. In other words, the troposphere is about 10 kilometers tall or so, approximately, to the nearest kilometer. We were already told the Brunt-Weissler frequency, the Coriolis parameter, and the beta term. So let's go ahead and go into the dispersion relationship. Okay, so we can put all the numbers in here. So anyway, here it is. Okay, and we gotta start working all these terms out. Now notice the units do have to work themselves out here. Okay, so notice that we put all these values in here, and then we have to start working these things out. Okay, so when we square 2 pi, we get 4 pi squared. Whenever we square n pi, we get n squared pi squared. Now, this right here is going to give you, let's see, that's 10 to the minus 1, but then here's 10 to the minus 4. And so when we work this up, we're going to get 10 to the minus 8, but then that drops to the bottom with 10 to the 8th. And then we square 10 to the minus 1, comes to the top. We're going to get 10 to the minus 6. Hopefully you can see that there. Okay? So hopefully, maybe you need me to go through that again, because this is going to be 10 to the minus 8 over 10 to the minus 2. So when you flip those and then go, you're just going to get 10 to the minus 6. Okay, so what we should actually have is we should get rid of this term, and then 1.5 to 10 to the minus 8 divided by 5,000 gives about 6.0 times 10 to the minus 12. And then we just got to start slugging through the rest of these things. Okay, so you can certainly use a calculator. There's nothing wrong with that. If I did this correctly, I do get this right here. And notice that this is an expression in terms of n and pi. I'm dividing everything here by pi, and I'm multiplying everything by 25 million here as well. So hopefully I'm getting something like this. Okay, so hopefully this roughly looks correct. Okay, so compared to the barotropic mode, now why is barotropic mode n equal to 0? Well, think about this. The barotropic mode, going back to here, the barotropic mode has no height dependence, just like this cosine function. Okay, so n equals to 0 is the 0th Fourier mode. That means the mode is independent, so the wave propagation speed and the dispersion relationship doesn't depend upon height at all. Okay, that's why it's barotropic mode. So the barotropic mode, n equals to 0. Notice that the angular frequency, unless the phase speed decreases, as n increases. Well, so think about this. If we put in 0 here, we just get basically omega over square root of k squared plus L squared for the wave speed. Now, how do I get that? Well, it turns out that the wave speed is going to be like the angular frequency. This, by the way, is the phase speed divided by the total wave number. Now, by the way, you need to add these things up in a Pythagorean sense. So it's k squared plus L squared square rooted. That's sort of like the total wave number. Okay? So if you put the values in, something like that, notice that, again, we're just going to let this right here equal to 0. Okay? So if you work this out, you get the phase speed for the barotropic mode is about 3.6 meters per second. N equals to 0. By the way, that's the magnitude, okay? Clearly this entire thing would be negative, so we know that Rossby waves propagate westward, okay, in the absence of background horizontal geostrophic velocity. So if capital U equals to 0, which we assumed in this case much earlier in the problem, then the phase speed would actually be negative. This would actually propagate towards the west, let's say, in the negative x direction. But we're just looking at magnitude here, so it's about 3.6 meters per second. Notice that if you put in n equals 1 there and then chug this through in your calculator, you get about 0.88 or so meters per second. So notice it's a lot slower. And think about why that is. So if you have stratification, the idea is that the waves aren't going to propagate so freely, because based upon the stratification, different parts of the wave, depending upon the height, are going to propagate at, well, different speeds. There's going to be more wave dispersion. So the barotropic mode propagates fastest, whereas baroclinic modes, this is the first baroclinic mode, okay? So the first baroclinic mode, that's n equals 1, that's going to propagate slower. So this is now the analysis of Rossby waves. So thanks for watching this, and I hope this all makes sense to you. So what we saw in this video is that we can understand Rossby waves, even if we're just looking at the mathematics, even if we're not looking at maps, even if we're not looking at weather observations, even if we're not trying to look at other sources and satellite data and all those kind of things. So Rossby waves are very, very important for weather forecasting in the middle latitudes. It's Rossby waves that typically carry the large weather systems, the large scale low and high pressure systems. Remember, quasi-geostrophic potential vorticity is how some of the first numerical weather prediction forecasts were made. And it turns out that quasi-geostrophic potential vorticity is a very nice way to formulate the equation so that you can go ahead and come up with a single predictive equation and then integrate that forward in time with a computer and come up with a reasonable solution. Remember, with quasi-geostrophic theory, there's lots of assumptions made. It's not as realistic of an atmosphere as you would like. So there are better approximations to the atmosphere, but those require more sophisticated equations, and that'll be discussed for another video. So I want to thank you for staying with me watching these videos. We're going to have links up here and links down in the description to the other parts of the videos in the playlist. And we'll certainly talk more about Rossby waves on this channel and more about atmospheric dynamics. Thank you for watching High Peak Education. Please smash that like button if you enjoy this content. Please subscribe to the channel to grow the channel. Social media links are down in the description below. Please support us on Patreon. And please share this video amongst your social networks. We appreciate it very much. Thank you for watching, and we'll see you in the next video.